And he was the first person to recognize it looks like light has energy that always seems to have a common factor. It's quantized. Energy is not continuous. The light energy coming off of a black body that's emitting radiation doesn't seem to be continuous. That was a huge discovery. And it was a discovery that Niels Bohr kind of built on when he came up with his first theory about electrons.
Black body, the sun,
I believe that the sun is considered a black body. I'm being recorded though, so I don't want to say too much. I'm not sure.
Yeah, because normally the second hour class is like a carnival.
What's up, Patrick?
We actually have to focus.
So this is an equation that you'll have to use. Energy equals H times R. Now this looks like a V. It's not a V though. What is it? You remember? Did this in Chem 1. Nu. This is nu. Greek letters.
What's new?
Yes. What's new? Yep. Yep. Energy is equal to Planck's constant times frequency. What this really is saying is that energy is directly related to frequency. When you have a wave, the more frequently the wave is occurring, that's a high frequency, that would have a high energy. That's what Max Planck was saying. If you have a low frequency, that has a low energy. The H is called Planck's constant. Why they didn't use P, I'll never know. They should have, if they called it Planck's constant. But somebody along the way thought it would be a good idea to use the letter H. Maybe that was Planck's middle initial. Yes?
626. You don't stitch? Ah, 626.
Yeah, and I just took the delta N out because it, I didn't like it there. And you won't use it. You will sometimes use this. You'll want to write down the value of H, because you'll need it. I will give you that. H is 6.63 times 10 to the negative 34th, if you can't read that negative 34th, joules per hertz. So it's a constant that really, and that H term is used in a lot of quantum mechanics. I mean, Planck came up with it. He's given credit for being a very, very smart person, pioneer in electromagnetic radiation. And that H term is used all over the place in these kinds of quantum studies. Then we have this guy. He was all physics, but he came up with discoveries in biology, chemistry, as well as physics. When he's given credit for being a brilliant scientist, he deserves all of it. He was a marvelous, brilliant person. Yeah. So he's best known for the special theory of relativity that relates energy to mass. And in the context of light waves, Einstein proposed that light, which really we think of as energy, just like a disturbance, he equates light waves as having a certain mass, which seems kind of dumb. You think, well, how can a light wave have mass? But it kind of behaves like a particle, and particles would have mass.
Wait, what's he calling?
Mr. Moore, you said that he discovered stuff in biology. Did he discover the bumblebee?
The bumblebee, you mean? Oh wait.
Well, it's a bee. It's a bee.
It's got wings. Yeah, a bunny has wings.
Bunny has legs.
I don't know what he was doing.
A bunny has legs.
Pretty famous picture of
It was a bunny.
He said he just told us bunny has legs.
I feel like it was
Go, Patrick.
like actually
Look what he's doing. Look what he's doing. Look what he's doing.
Oh, have you?
Little people, I will teach you history.
Wait, Mr.
You don't know
Maybe
squat.
you photoshopped it to make physicists look idiotic.
I just said all kinds of nice things about it.
Whoa. To detract attention
No, he
from
was
your
all
true
physics.
personality.
Yeah, he did. But yeah, he was still called a physicist.
Do something like
All right, so now from Max Planck we have E equals h nu. From Einstein we have E equals mc squared. Well, therefore, h nu must equals mc squared. So just putting those two together, working this out and solving for this right here, just putting the mass on one side and the others, all the others on the other side. Mass is equal to h times nu over c squared. Now mass of what? This is equivalent mass of light waves. Light waves have a mass that's equal to these things. A constant times frequency over a constant. So the higher the frequency of light, the higher the equivalent mass of it would be. And I'm using the word equivalent because could you put light on a balance and get the mass up? Well, no. But it is a form of energy, and at the quantum level, this is not true in our macroscopic world. We know nothing about this, but in our real world experience. But if you're on the atomic level, then you would get knocked over by a light wave. You could get knocked over by a light wave because it's like a particle flying around. Now, and just one other thing was done with this. We know another relationship that involves light. Haven't mentioned it yet, but this one is one of our fundamental units of light, or not units, but equations of light. Speed of light equals wavelength times frequency. That's lambda times nu. Now, given this, solving it for nu is equal to c over lambda.
Lambda?
Yeah. That's Vibob's attempt to be funny. What's new, right? C over lambda. Oh yeah, sure. All right, so if we took that nu and we substituted this term in for that nu, it's going to look like this. Mass of light equals h times c over lambda over c squared. And then just cleaning this up a bit, I can lose one of the carbons. See, here I'm talking chemistry. One of the c's, the speed of light terms. And so mass equals, I can't believe I said carbon. H over lambda times c. So that means that, and this is just a little bitty equation relating mass of light to its wavelength. Wavelength is easier for us to measure. You can run filter out light and read what its wavelength is with a spectroscope. And so it's a little bit easier to use than frequency. So this gives us the mass of a light wave. The mass of a light wave. A while later, in the 1920s, there's a French guy. An American would call him Louis de Broglie. The French people, his mother would have called him Louis de Broglie.
That's how Donald Trump would pronounce it.
What? Now, de Broglie came up with a parallel concept to what Einstein had 15 or so years before. A little more than I was about 15 years before. De Broglie, he derived this relationship for non-quantum particles, like particles that actually could be measured and aren't really, really tiny and small. I guess they're usually still used to be pretty small, but this refers to a particle like an electron or a proton or a neutron. It's traveling at speeds that are not necessarily the speed of light. Now, I apologize for this. This thing, I've been using a nu to represent frequency, which looks like a V. Now I have to use a V for the de Broglie equation. This is a V. It represents a velocity not at the speed of light. And when you compare this relationship to what Einstein had on the previous page, They're very simple. They're parallel ideas. This is saying a particle has properties of light waves. And Einstein was saying light waves have properties of particles, like mass. So at the quantum level, it's a world that we don't know much about. I mean, we in the human world.
That's like the same line they say on every single Nobel program.
Yeah, yeah.
It's like
Yeah.
so cliche.
Yeah, yeah. It's just kind of weird that so much is going on that we wouldn't know.
All speculation.
They got me really hyped up with those Nova channels when I was like in middle school. Now I'm like, I don't care anymore. They like advertise it so much.
Yeah. So write this one down. I know there are exercises in the chapter there that ask for what is the wavelength associated with a neutron that's going like 90% the speed of light or whatever the broad equation. Yeah.
There's other problems this weekend, like, do we go and-
Oh yeah. This weekend, absolutely, you do lots of. No. You do quite a few of them. Now we're still doing physics. This is Niels Bohr. We're getting closer to chemistry with what Niels Bohr did, but it's still 100% physics. Bohr was the first person given credit for describing the energy of electrons. Yeah, the energy of electrons being quantized. Max Planck came up with the idea that energy can be quantized, but didn't relate it to atoms. Bohr was the first person to take Planck's work and say, hey, that quantized idea, that must be referring to the electrons jumping, and light must be caused from the electrons jumping. Niels Bohr observed the emission spectrum of hydrogen, produced only a few bright lines, not a continuous spectrum. That was what Planck was observing with the black body.
And they're gonna be like that and stuff the other day. You know what I mean? Super screwed.
They all know all of this. They can't know all of this.
Yeah.
Like on the quiz.
I thought you liked physics, Justin. More practical physics, not so much theoretical. This is all theoretical physics.
Like Galactic schools will take them over. Yeah. From first day of first semester. It's just But yeah, you should do it for the test.
You don't need it.
Oh, it takes one out of three.
All right, can I have you look up here, please? This is a very simplified model of what Bohr was saying. Bohr is saying, okay, here are three energy levels for electrons. You have an energy level right there, and right there. There's three energy levels. You name them N values. The electron of hydrogen, he's looking at the electron of hydrogen. So the electron can have that much energy and be that distance from the nucleus. But it could also gain energy and jump up to that one.